Good morning, chemists. Good morning. How are you guys? Are you enjoying our break from lab? Remember, no lab today, no lab tomorrow. You guys there? Okay, there we go. My internet might have gone out for a second. Uh-oh, I forgot to put on earrings today. Excuse my ears being blank. Anyway, so let's get into our chapter 16. So we're chapter 16, section 4 now. So talking about our electrophilic aromatic substitution reactions. Are you guys there? I don't know if this is working. Hold on. If you guys can hear me, please say something in the chat.
Yeah, we can hear and
I
see
can't
you.
see you guys. You can hear me? Okay. I don't know why I can't see a single one of you.
Can you hear us?
Okay, well, that's fine then. I'll just ignore that I can't see you. All right, anyway, so 16-4, we're talking about our electrophilic aromatic substitution reactions. We said that we need our benzene ring to really be activated, so some kind of electron donating group on the ring to activate it, right? That's what activates it, something that can donate in electron density, but something deactivates by withdrawing electron density, pulls electron density out, makes it electron poor, and so it's not going to be as fast of a reaction, but the reaction can still occur. So we've talked about if we have one thing on the ring, where is the next thing going to go? Ortho, para, or to the meta position, depending on if we have an ortho para director or a meta director. Then we are going to add in now, what happens if we have two things already on the ring and we're adding in a third thing? So for our two things on the ring now we have a competition. So when we're looking at two things already on the ring, whatever is the strongest activator, that's going to dictate what happens. The strongest activator dictates what happens in the reaction. So remember that our ortho para directors, these are activators. And so with those there, we're going to have the reaction happen at the ortho and para position. So let's look at our first example here. We have OH and we have CH3. We know this is a strong activator, and we know this is a weak activator. They're both activators, but the strongest activator dictates the course of the reaction. Notice that the para position is blocked by the methyl. So even though this is an ortho para director, there's only an ortho position open. So ortho on either side would be the same exact thing. So they're just showing you one spot, but remember there are two equivalent ortho positions. So really one product. It doesn't matter if you put it ortho on the left or on the right, same product. All right, let's look at our next example. Here we have nitro. Nitro is a deactivator, and really a strong deactivator. We want the strongest activator. Do we have an activator here? Yes. Our activator is a weak activator. This is what's going to dictate, and it's an ortho para director, so that's going to dictate the course of the reaction. Again, ortho is blocked by the, para is blocked by the nitro, but we have these ortho positions. Again, two equivalent ortho positions there. Looking at our next example. So you just have to kind of look at these and just know this is an ortho para director. This is a meta director. You have to just know that kind of stuff as you look at the ring. When we have here a strong deactivator in the carboxylic acid group, and we have a nitrogen, remember that nitrogen has a lone pair on it, this is a strong activator. This is what will dictate the course of the reaction. It's an ortho para director. So the ortho position that's open and the para position, both of those will react. We'll get one product. Remember how nitrogen, that NH2 is super reactive, so all open spots will react. That's what will happen here. And then here we have a strong activator. Actually kind of moderate. I'm going to say moderate here. It's a better term for this one. We have a moderate activator, and then we have a weak deactivator. We know that the bromine can deactivate, but as it deactivates, it's going to be an ortho pair director. But we want our strongest activator. So our strongest activator is the methoxy. It's an ortho pair director. So the ortho spots and the para spot, the para position, these can all react. Now, if we only had meta directors, yeah, they deactivate the ring, but remember, it can still happen. So it's going to slow the reaction down. And so if there's only meta directors, it'll slow it down and it'll only happen at the meta position. Here we have a strong deactivator. This is going to slow down the reaction a little bit. But remember, the strongest activator is still dictating the course of the reaction. This is going to slow down the reaction a little bit, slow the substitution of the ortho pair positions, but it will also, if there's the only thing there, then remember it'll be a meta director. So they have color coded this, but remember you do have this, this that you need to be considering here as we look at what is a strong moderate activator, deactivator, and then orthopara / meta director. So make sure you spend some time looking at this chart. Questions there? All right, so for our reaction, now we can kind of put our substituents into different categories based on their directing power. We have our nitrogen and oxygen as our strongest directors. Then we have our halogen and alkyl groups. And then we have our meta directors. And so any kind of a higher group there is going to override the directing power of lower ranking groups, just like we saw before. If we have a really strong activator and a weak deactivator, the strong activator will dictate the course of the reaction. If we have members of the same group, though, if they're in the same group, now there's going to be a competition. And so we're going to get a mixture of isomeric products if they're in the same group. So what do I mean by that? We have bromine and bromine. They're both weak deactivators, but orthopara directors. And so both of them are orthopara directors. The para position is blocked for either one, but the ortho position for this bromine and the ortho position for this bromine, ortho to this bromine, those are places where the reaction can occur. These are equivalent though, right? All four of these ortho positions are equivalent, so they only marked one of them. So same thing with these two alkyls. These are both weak activators and orthopara directors, weak activators and orthopara directors. And so with these now, this is not going to be equivalent, right? We have ortho to the methyl and then ortho to the ethyl. So we're going to get two products, whereas here we only would get one product because all four of those spots are equivalent. So we know that ortho on either side, that would be equivalent, ortho to the ethyl, and we know ortho to the methyl, so we get two products that could form here. Here we have these two methoxys, and so with these two methoxys, we know that these are moderate activators. And so with these ortho-para directors, the reaction can be para to this methoxy. It can be para to this methoxy. It can be ortho to this methoxy. It can be ortho to this methoxy. But it ends up that with these, we only have these two positions that are going to be new. The other products would be the exact same thing. If we flipped it, it would be the exact same thing. So we would get two unique products. So you can draw all the products there to satisfy your mind, but it would be the exact same thing because this is symmetrical. We have two of the exact same groups there, methoxy. Here we have two deactivators. And so they're strong deactivators. So this is going to be a slow reaction. And with it, they're both going to be meta directors. So it can be meta to the carboxylic acid or meta to the nitro. They are meta to each other, so there's only one meta position available. So you get one product here. Here we have two strong deactivators. So same thing here as we saw here. They're both meta directors. So meta to this carboxylic acid, and then meta to this carboxylic acid. And then we could do it on the other side, but again, that would be the exact same thing. So here we would get two products, two unique products there. Questions on this? All right, so there's something else we have to consider. We have to think about our sterics. So with sterics, if we have something trying to attack, we want to try to bring in an electrophile right beside, so in the ortho position, to something that's kind of bulky or in between two groups, that's going to be slow or it won't even happen. So in this class, we'll just say it doesn't happen. So it's going to be a minor product. So I'll ask you for major products. We'll count these as minor products that you don't have to draw. So what do we have here in our first example? We have a small methyl and we have a bulky T-butyl group. And so with the bulky T-butyl group, they're both ortho pair directors, right? So we have the ortho position, these two would be equivalent, and we have our ortho position here, these two on both sides would be equivalent. But where you see this dash line, that means it's not going to add there. Because of the bulk of the T-butyl group, it's going to be too sterically hindered for us to bring in a group there. There's no way we can rotate around those three methyls so that we have a hydrogen on one side so that we can bring in that electrophile easier. So we're not going to have the reaction happen there. So we're only going to get one product as our major product here, where it is ortho to the small methyl. Here we have a small methyl and a chlorine, but in between the two, we're not going to have the reaction happen. Our strongest activator will dictate the course of the reaction. What's our strongest activator? It's this weak activator. That's what's going to dictate the reaction, not our weak deactivator. The weak deactivator is not dictating the reaction, not directing the reaction. So for our weak activator, we have the para position and the ortho position for with respect to the methyl, our weak activator. The strongest activator is what dictates the reaction. So we can't have this ortho position that is blocked by sterics. Here at methoxy and ethoxy, again, sterics will block. Both of them are going to direct. They both are directing the course of the reaction. So we can have ortho to the methoxy right here. We can have para to the methoxy. We can have ortho to the ethoxy, and we can have para to the ethoxy. So both of those are possible. But remember, like I said, both of these are in the same group. And so they are both going to direct to the ortho and para position. So we get a mixture of products. But they both end up having the exact same products for the ortho and para substitution. All right, and then finally here, this group, the sulfonyl group, that is bulky. Just always take that as a bulky group. And so what kind of a director is it? This is a meta director. It is a deactivator. So for this meta director, we can have the reaction happen meta to either one of these sulfonyl groups, but because this is bulky, we're not going to have it meta where it ends up ortho to a bulky group because it would be right beside a bulky group. So we'd only have one product that could form here, where it would be meta to the sulfonyl group that I underlined. And the other sulfonyl, but on the other side. Questions on this? All right, so that's where if we have two groups already on the ring, we have a di-substituted benzene. What if we have multiple groups? When we add in more and more groups and we try to continue doing more electrophilic aromatic substitution reactions, there are fewer open spots, fewer places where we can put substituents. So let's look at this. What's our strongest activator here? The amino group is our strongest activator. So the amino group, it's an ortho para director. Para is blocked because there's already something there. Ortho is blocked because of steric hindrance on one side, so we can only get one product, where the other ortho position is what is reacting. What's our strongest activator here? The methyl. We can't react here at this ortho, we can't react here at the para, but we can do this ortho. So we, again, only get one product possible here. Strongest activator in this case, again, the nitrogen. Ortho, ortho, both blocked. So the only thing that we can do is add something into the para position. Here we have three groups. They are all directing the reaction. They can all have the reaction happen ortho or para to them. So let's see, ortho to either of these methyls would be blocked by sterics. Here, this is bulky, so ortho to that would also be blocked by sterics. So the only position open, there's only one product possible here, where we are reacting and we are para to this methyl and ortho to this methyl. That's all that's possible. Questions here?
So even when it's just two methyls, like they're small groups, it's still blocked by sterics?
Because it's in between the two of them, yes. It's slow, so we would say that reaction would be slow, but just so that we can just have everything be in between these two, let's just have it blocked. I'm just going to say minor enough that we're going to ignore it, just to kind of streamline it for you. All right, so this is 16-5. So we talked about our nitro and our amino group, right? We've already discussed both of those groups. And so the way that we can put a nitrogen onto a benzene ring is by the nitration reaction. So we know how to do the nitration reaction. We have our benzene ring, we have our HNO3, and we have our H2SO4. So with that, we can make a nitro benzene. But nitro is a deactivator and a meta director. So if the next reaction that you want to do is where you want to have an activator and an ortho para director on there, then you need to convert that nitro into an amino group. And so for our nitro group, it's a meta director. How do we turn that into an amino, an ortho para director? We can do any of these reactions here. So this is a reduction. This is a nitro reduction. So what is a reduction? Losing bonds to oxygen. What's an oxidation? Gaining bonds to oxygen. You should already know that. We talked about that last semester. So a nitro reduction, we can do, so let me point out these two. These are two reduction. We've seen these before, right? When we were doing reduction of the double bond to single bond or triple bond to single bond, we've seen these before. Here we have another one where we use this zinc amalgam in HCl. And then here we use iron metal with HCl. So those are four different possibilities. Note all four. They can all be used interchangeably for the nitro reduction to get the amino group. What if we want to do the oxidation though? Well, look at what we have here. A peroxy carboxylic acid. Specifically, peroxyacetic acid. And so for this trifluoroperoxyacetic acid, we're doing this oxidation now. We said two oxygen bonds. This has a lot of oxygens there. We can use this for an oxidation. Think back to MCPBA. We were doing an oxidation there, adding in an oxygen to a double bond. And so here we're doing an oxidation again, where we're adding in these oxygens for the nitro group. So where would this be necessary? Well, let's say we want to make M-bromoaniline. Common name here, right? M-bromoaniline. If we want to make that, if that's what we want, we know that this is an ortho-para director, but it's an activator, right? And we know that this is also an ortho-para director. So neither one of them, if they're on there first, neither one of them will direct it to be in the meta position, will direct the reaction to occur meta to the other. So what do we have to have on there first? We have to have a nitro group on there first. Then we do a bromination. So sure, we probably have to heat this up because this is a deactivated ring. But we can do the reaction. So we heat it up, get the meta disubstituted product. And then with that, now we can do our nitro reduction. Nitro to the amino group. It's the only way to access this product, this specific product. We also talked about our Friedelcrafts alkylations and acylations, and we said that Friedelcrafts alkylations have a lot of problems with them, right? So think back to the problems we had with those Friedelcrafts alkylations, and so we did this multi-step process. Think back to the end of last chapter. We did a multi-step process where we added in an acyl group, and then we basically did some reductions to lose bonds to oxygen, and then we had our, in the end, our alkyl chain. So that's a multi-step process. We can do it in one step though. So with our starting material, so we did our Friedelcrafts. So we'll have R on here and Cl. So we'll say AlCl3. With this, our Friedelcrafts Isolation, we can put our acyl group on there. And so with this acyl group on there, now we can do a reduction, right? We're losing bonds to oxygen. And so we reduce this to where this carbon, I'll call this 1, I'll call R2. Carbon 1 ends up having 2 bonds to hydrogen now instead of a double bond to oxygen. So we can change this into an alkyl group by doing what's called a Clemmensen reduction. This is the Clemmensen reduction, this zinc reaction. Or we can do a palladium catalyzed hydrogenation. Hydrogen, palladium, and then here the solvent, ethanol. That all can be used, so don't forget where there's heat needed, but that all can be used for the reduction. Oxidation, we've seen this before. We saw this last semester for oxidation. This is just one of those chromium reagents for oxidation. So remember we saw like Na2, Cr2, O7, but here we have CrO3 specifically, H2SO4, and water. Here we can do the oxidation here with chromium trioxide. It's specifically going to oxidize the benzylic carbon. What's the benzylic carbon? The one right beside the benzene ring. So we can do this reaction here. Similar reagents to what we saw with the nitro reductions though. Notice the similarities there. That'll help you to memorize these. All right, so why would we use our Friedelcrafts Isolation? So here we have our Friedelcrafts Isolation. We have our chlorination. What kind of a director is this? This is going to be a meta director. It's a deactivator. And so with this deactivator, we might need to heat it up to have the reaction go, but we can have it occur where these two groups are meta to one another. And then we can do our reduction. And so with our reduction here, they're using the palladium and ethanol, but we end up with this meta-disubstituted product where, again, both of these are ortho-para directors. Both of these are ortho-para directors, so we couldn't have done this otherwise. So you have to be kind of smart about what group you add in when and in what order because of how we know these are going to direct future electrophilic aromatic substitution reactions. So as I said, we can avoid doing that multi-step process by doing here now a two-step process. Step 1 is the Friedelcrafts Isolation. And then step 2 is the reduction. Instead of trying to do a Friedelcrafts alkylation, because remember we can do over-alkylations, and then remember the rearrangements that were possible with the Friedelcrafts alkylations, we can avoid those by doing now this two-step process. Friedelcrafts isolation and reduction. Questions there? All right, so with our reactions, remember we can do the Friedelcrafts alkylation, it just has issues, but it's possible. And our Friedelcrafts isolation, it's not going to happen if there's already something there that is strongly deactivating the ring. So we don't want to have that on there first. So look at this series. They have these two steps down below. So starting with benzene, are we going to do the Friedelcrafts? I'll do it this way. Are we going to do the Friedelcrafts isolation first and then the nitration? Or are you going to do the nitration first and then the Friedelcrafts isolation? That's what we're seeing here. So what's better? It's better to do the Friedelcrafts isolation first because a strongly deactivating nitro group cannot be present before Friedelcrafts isolation. We can't have the nitro group there first, so we cannot do this reaction where we put the nitro group on first. The nitro group can come on, but it has to come on in the second step because the nitro group is too deactivating. So you have to just be careful with the order when you're doing your Friedelcrafts alkylations and isolations. All right. So then we can also talk about those Friedelcrafts isolations. We just said we can't do them in the presence of nitro groups, but what about halogens? Well, the halogens are weak deactivators. And so if they are weak deactivators, this can occur. The Friedelcrafts isolation can occur. So here you see the Friedelcrafts isolation over here on the side. We have a halogen there. We know it's an ortho-para director. And so we do our Friedelcrafts isolation here. This reaction occurs, high yield para product, because we know about para being major in most cases. Here we're doing a Friedelcrafts alkylation though. What's our mechanism here? Well, you know this mechanism. We lose water, multi-step process, we lose water, and so we end up with this secondary carbocation. So whatever is on that ring, you know that the first step is that you, from the middle of the double bond, attack that carbocation. That's our electrophile. Yeah, there are other things on the ring, but this is the reaction that we would have where 1, 2, 3, carbon 2 is bonded to the ring. So this reaction can occur with the chlorine there. And then here, look, we have a nitro. We said we don't want to have the nitro on there first, but we have this strong activator there. And so when we have an activating substituent present, the effect of the deactivator can be canceled out. So that's what we're looking at down below. All right, here we have this bulky T-butyl group, and we want to do a nitration with it. So let's look at the product mixture. Because this is bulky, obviously our product, our major product is going to be 73% yield here, where we are doing para disubstituted, making the para disubstituted product. Because we know this is bulky, and so there's going to be some steric hindrance here. So a really low yield for this, and we know meta is going to be minor. But we know it's an ortho-para director, but it's going to, since it's so bulky, direct into the para position. But what if you want the product that's ortho disubstituted? What if you want the ortho product. You only get 16% yield, so how can we increase the yield? Well, we can do this multi-step process. So we have our bulky group here, but it's an ortho para director. When we do this next step, a sulfonation, now we can add this sulfonyl group. It'll only add into the para position because these two are bulky. They want to stay as far away from each other as possible. Now when we do the nitration, still the strongest activator is going to dictate the reaction. So our T-butyl group dictates the course of the reaction. Para is blocked by our blocking group. The sulfonyl group is a blocking group. It's blocking the para position, so the reaction can only happen in the ortho position. Then we can do this step where we are removing the sulfonyl. We remove that sulfonyl group, giving us a high yield of the ortho disubstituted product, none of the para. The para couldn't happen because we blocked the para position with our sulfonyl group. So the sulfonyl group is a reversible sulfonation. We talked about this last chapter. You put it on and then you can take it back off with this aqueous workup with heat. That allows you to block certain positions where you don't want the reaction to occur, so you can force groups into other positions that it still wants to direct it to, but it just can't direct it to the para position here. Questions on this? All right, our last thing that we need to think about is how we use our phenol and our aniline. So remember, phenol and aniline are very, very reactive. And so remember, for both of those, we would have polysubstitutions. All open ortho and para positions will react, and you'll get a polysubstituted product. And so instead, we can use protecting groups. We can kind of lower, we're moderating the activating power of these groups by changing them into other things. So here we have our phenol, we change it into methoxybenzene. How are we doing that? This is an SN2 reaction. You saw this reaction before. We use base first to deprotonate the acidic hydrogen here. Base deprotonates, now you make a good nucleophile. With that good nucleophile, now that can react with our methyl iodide, giving methoxybenzene. If you want to remove it, concentrated acid, again, you know this reaction. This is an ether. So from chapter 9, we talked about ether, turning the ether back into an alcohol. So you know how to do this reaction. So that's something that we can do. We can also have our aniline and turn it into acid aniline. And so what do we use here? We use one of our acyl chlorides. So this is acetyl chloride here. Remember, that's an acetyl group. And so with this, we use this thing called pyridine. I'm going to draw pyridine for you just so you know what it is. Pyridine is just like benzene, except there's a nitrogen in the ring. So this is something that you wouldn't see until section 20-2, but you can look ahead and look at this mechanism for how this is occurring. But the nitrogen ends up having now this acetyl group, and we talked about how this is pulling away electron density. And so instead of having this this lone pair that we have available to just push into the ring, it can be pushed into the ring, but it can also be pushed up into that group. We talked about this before. Lone pair into this bond up to the oxygen. And so we end up with this resonance form where now oxygen has a negative charge, nitrogen has a positive charge. So we've pulled out electron density as we push it onto our oxygen. So we've kind of tempered the ability of that nitrogen to donate in its electron density. So now this is a strong activator, very strong activator, and this is still a strong activator, but we'll call this kind of moderate. So now we're not going to have the reaction happen at all open spots. Now the reaction would only happen at our para position because we're doing this sulfonation, bulky group. It wants to go into away from this kind of bulky nitrogen substituent. Then we could do our nitration. The only thing open is the ortho position. And now we do a two-step process. So what's happening in step one here? In step one here, we have our aqueous acid. The aqueous acid is going to remove sulfonyl. And then what's happening in step two? In step two here, this is going to do a base hydrolysis of the acetyl protecting group. So two-step process. One thing removes this and the other removes this. Those both get removed in that next step so that we end up with our ortho-nitroaniline product. So we're using that blocking procedure and we're using protecting groups. Questions on this?
So the sulfonate group only goes to the pair position because it's a moderate activator?
No, yeah, so it could happen if we had tried to do it here, then it would be possible that we'd have it added to both the ortho and the para position, all three positions in one product. But yeah, because now we've kind of moderated it, we've kind of toned down the activating nature of that nitrogen. Now we're only going to add to ortho or para, but we only get para because this is a bulky group. And then we can have only ortho because we're blocking the para position. All right, so that's the end. You can see reactions that we learned about in chapter 15, and now we talked about a few more in chapter 16. Let's get into our learning checks. All right, so what's most reactive to the electrophilic aromatic substitution? What do we want it to be? We want it to be electron rich. Electron rich. So we have these three fluorines here. We know those three fluorines are going to be pulling away electron density, and they're going to pull electron density out of the ring. So we know this is going to be electron poor. We know that, again, over here, same thing, but we don't have as many groups pulling away. For this trifluoro group, we know that each of these fluorines will be pulling electron density toward itself. And so this is going to be very electron poor, whereas this is just going to be electron poor. Remember, these fluorines are electron withdrawing groups by induction. This is an electron withdrawing group by induction. But here we have a methyl that can donate an electron density. That's an electron donating group by induction. There's no lone pair. We can't do resonance. So what compound is going to be best here is going to be most reactive. And this one is going to be least reactive. It could still occur, but it's least reactive. Questions on this? All right, same thing. What's most reactive? So here we have a nitrogen. When nitrogen makes 4 bonds, it has 0 lone pairs, right? We can see that octet rule. And so it has a positive charge. But when nitrogen makes 3 bonds, it has 1 lone pair, and it is neutral. So here we have a nitrogen with a positive charge. Here we have a nitrogen that's neutral. So we know it has to have a lone pair on it. And so what do we know about that? We know that that can donate in electron density, making this ring electron rich. This is an electron donating group by resonance. This is an electron donating group just by polarity. Just because an sp2 carbon is pulling away electron density from an sp3 carbon. So this is an electron donating group, but just by induction. Which one's better? Electron donating by resonance is better. So they're both electron rich, but this is more so, right? We get a resonance form where we put a negative charge on this carbon. That carbon gets a full negative charge, so that's better. Now, how does that compare to this nitrogen? Well, nitrogen hates having a positive charge. So if it hates having a positive charge, remember that all nitrogens are electron withdrawing groups by induction. So that what we're seeing here for this nitrogen is also true for this nitrogen. It's just that it can also do electron donation. So it's an electron withdrawing group by induction. If it has a positive charge, it hates having a positive charge. It's pulling away electron density from everything beside it, so that if something comes to take something away, it can keep those electrons and become neutral. So this is very electron poor. So what's going to have our fastest rate? What's most reactive? This is most reactive because we end up with a resonance form where we have a lone pair and a negative charge. This is a very good nucleophile that can be used in an electrophilic aromatic substitution, right? That's what we needed to do. We need to go attack an electrophile. So this is going to be most reactive, and this is least reactive. Questions here? All right. So then we have here a reaction. And so what are we going to be doing in each of these steps? So we have a phenol. We know with phenol, this is very activated. Very activated. So what happens in this step? We add in some base. We know when we add in base, we're going to get this alkoxide ion. And then we have our carbon with a bond to iodide. We're doing an SN2 reaction. And so we end up with methoxybenzene. Now it's not as activated. So this is strongly activated. And this is moderately. Then we do our next step, the nitration. And so what is this? This is an ortho-para director. And so what product or products will we get? Well, we'll get two products, actually. One product is this, where we've added the nitro group to one of those ortho positions. And then we'll get another product there, where we've added the nitro. Remember, it's a bond between carbon and nitrogen, and then oxygens are over to the side. We've added the nitro to the para position. Most likely the para position is the major product, but we'll count both of these as the major products here. Meta is minor. Why did we do this two-step process? Well, let's look at what would have happened if we had done it as a one-step process. What if we had done this? What product or products would we have gotten here? Well, we would have gotten one product where all open ortho and para positions would react. So that's why we have to do this two-step process and make it moderately activated. Questions there?
I have a question.
Uh-huh.
The product that is in the para position, you mentioned that that would technically be the major product. Is that because of steric hindrance?
Correct.
Okay,
Yeah.
thank you.
Uh-huh. All right. So now we have another reaction. I want to bring to your memory, though, that there is a hydrogen here. So even though this is bulky, there is still a little bit of space where we can kind of rotate a hydrogen around, but it's still a bulky group. So a bulky group, we do a sulfonation. We add our sulfonyl group in there. What's that going to look like? Well, we will get our sulfur. It's a carbon-sulfur bond. And then over to the side, we have 3 oxygens and a hydrogen. Remember, this was an ortho-para director. So now we have 2 bulky groups, but one bulky group is a little bit less bulky and is our director. That's our ortho-para director because this is a deactivator. Our strongest activator wins. So here we have a weak activator, but it's still going to win. So we do a Friedelcrafts Isolation. We see our aluminum chloride, we see our acyl chloride or acetyl chloride. So we're doing a Friedelcrafts Isolation. And so here is our product. So what are we going to do? We're going to add it to the ortho position. It doesn't matter which ortho position you add the group to. Honestly, it doesn't matter. They're both the exact same. Oh, let me add it to the other side because I don't have any space here. But if you had added it to that other ortho position, it's totally fine. So we have this acetyl group that we've added. So with this, though, there's something else. Look at this. It's Friedelcrafts Isolation. There is complex to that, aluminum and chlorine. That's complex. So we always need an aqueous workup step. So this step is kind of two-pronged. This step does 2 things. One thing that it does is it removes the aluminum chloride. And then the other thing that this step does, look at it, aqueous workup with the heat. So now this is going to remove the sulfonyl group also. 2 things happen in one step. And so we end up with this as our product, as our only product. Questions there? All right. Here we have a multi-step procedure. So we got to track as we're going through to see what's happening in each step. All right, so this is a deactivator and it's a meta director. We have heat here because the ring is deactivated for further reaction, but it can occur. Nitro group is already there. We're going to add chlorine to the meta position. Now, what's this next step? Iron, HCl, nitro reduction. So our nitro group becomes an amino group. Remember, we couldn't have accessed this if we had tried to just have the amine there in the beginning. We had to have a meta director if we want the meta disubstituted product. All right, so now we have an acyl chloride But notice it's not aluminum chloride, it's pyridine. Pay careful attention there. We are not doing a Friedelcrafts Isolation. This is not a Friedelcrafts Isolation. Pay close attention. If there is pyridine there, then that means that we are adding to our nitrogen this acetyl group. So we go from this amino group that is strongly activated to now it's moderately. Now it's moderately activated. All right, I'm going to go to another slide just because I need more space, but it's the same steps. I'm just on the next slide just so I can write everything out. I need a bit more space, but I can go back if you guys need me to after we finish. All right, so this is where we're at. We've put on this moderately activating group. That's going to dictate the reaction. This is directing our reaction. So everything is going to be ortho and para to this. So let's look at our different positions that we have. Can we do the reaction in these different spots? We're not going to react here in that ortho position because it's blocked by sterics. But we can do the reaction here, para to the nitrogen, and we can do the reaction here, ortho on this side to the nitrogen. So we're going to get two products. So nitration, so we add a nitro group into the para position, and then we're going to add a nitro group into that ortho position. Only two products possible. So now with this, what's our next step? NaOH and water. So we have base and water. What happens here? We're going to be removing, or we could say we're using base to hydrolyze the acetyl group, the acetyl protecting group. So if we remove that group and the two products, would look like this. Questions here? Or do you need me to go back to show you the previous slide?
Yeah, Professor, can we please go back to the previous?
Yeah. All right, let's move on. One last one. We want to predict the major product following nitration. So just do the nitration reaction. What's nitration? HNO3, H2SO4. We're adding it to each of these. What's going to happen? All right, so with this one, we have a, and you have to recognize the nitrogen's pulling away electron density. So you have a very strong deactivator and a deactivator. So it's still maybe moderate, but we'll just call it a strong deactivator, but it's moderate. It's not as strong as the other one. So we have two strong deactivators. They're both meta directors. And so if they're both meta directors, each one of them can direct the reaction meta to it. But for this, they're meta to one another, and so there's only one open position there. And so the only open position is meta to both of them. So we only get, oops, not NO3. We only get one product there. Sorry, NO2. Meta to both of them. All right, let's do the next one. Here we have an ethyl. This is an ortho para director. It's only one thing on there. So the reaction can happen ortho to the ethyl and para to the ethyl. Two products. Ortho and para. Next one, fluorine, weak deactivator, nitrogen, strong activator, not as strong as if it was NH2, right? These are two methyls. So here we're fine, but our ortho, we know it's an ortho and para director. Both orthos are blocked by something already being there, so we only get one possible product. The only product that we can form is where that nitro was added to the para position. Because the ortho positions are blocked. But if they weren't, then yeah, we could get more than one product there. All right, and then our last one here, nitrogen, lone pair on it, strong, this is our strongest activator. And then we have an ester, it's a deactivator. It's pulling away electron density, right? Based on resonance, this is an electron withdrawing group by resonance. But this is an electron donating group by resonance. Strongest activator wins. So what are we going to do? Ortho and para positions. We know that this is blocked by sterics. So all we have is ortho to the amine and para to the amine. The amine is directing the reaction. Because that is such a strong activator, we're going to get only one product. Because it's NH2, we're going to get only one product where the nitro has been added to the ortho and the para positions. Only one product formed there. If we had changed it into the nitrogen with the acetyl group, acid analyte, then we could have tempered it, taken down that activation a little bit, but because it is a nitrogen with two hydrogens on it, that lone pair is ready to donate an electron density. So both the ortho and the para position will react. One product formed here. Questions on any of these, or you need me to go back to any of them?
Could you go back to the first one? Oh, sorry.
I'll just go back through them slowly. So this is our first one. Here's our second one. Here's our third one. And then here's the last one. You want me to go back again or talk about any of them?
On the last one, on this one, can you explain again why there's only one product?
Because this is our strongest activator, the amine. And so remember, with OH or NH2 on the ring, all open ortho and para positions will react. So remember, we talked about that with the phenol here. All open ortho and para positions will react. And so we temper it by turning the phenol into the methoxy, or by turning the, I don't remember if we did one of these. Here, yeah, by turning it into the acid analyte to temper it. So it would only react in the ortho and para position. But here it's not tempered. Oops. It's not tempered. It's not toned down. It's going to react in all open spots. All right, you guys, well, that's the end of this chapter. This isn't going to be on this exam. It's going to be on the next exam. But, I mean, obviously, it kind of is on this exam, right? These are the reactions we learned about in chapter 15. We just applied them further. But remember that we have, you'll have your problem set. I'll give it to you today, and it'll be due on Friday. But remember, you have your exam and learning assessments next week. And we will be back in the lab. But remember, your lab report isn't due until next week. All right, you guys, have a great day. If you do have questions, I have a few minutes. I can stick around. But have a great day, and I will see you guys on Friday. No lab. See you Friday.
Thank you.
You're welcome. Bye, you guys.